relates to not just today's experiment, but tomorrow's experiment as well. So I think we're going to go over this example here. Again, it's from your lecture notes, and then we'll stop there, and then we'll talk about the experiment, obviously, and stuff like that. So we'll just kind of continue on just to make sure, again, everybody's on the same page and how to do these calculations that involve buffers and sort of what's going on. So again, make sure you put here, and then for now, why don't you take some little bit of time here and come up with what you think the answer is here for this. There's actually two questions on this one. We want to know what is the pH of the buffer to begin with before we do anything to it. And then we want to know what will the pH be after we add, looks like 20 milliliters of sodium hydroxide in this case, to 80 milliliters of the buffer. So you want to approach it very similar to how we did the last example there in lecture. I will tell you a couple of things as well. The volume here is not being held constant, so you do need to take the volumes into account. So here again, we're adding 20 milliliters of sodium hydroxide to 80 milliliters of the beaker. So again, give it a try, see what you come up with. Again, two answers. One, what is the pH of just the buffer by itself before you do anything to it? And then what is the pH after you add the sodium hydroxide? And again, remember, just like we talked about, whenever you're doing anything that involves adding volumes and you're doing an ice table, make sure you let me also give you a piece of information that might be helpful, I suppose. Yes, sorry. Ka for NH4 plus 5.6 times 10 to the minus 10. You make it what is sort of your pH of it, the baseline sort of pH where it's starting. So a couple of things, as we talked about before, that you want to think about when you're looking at these problems. Again, not all problems will, straight out tell you, hey, this is a buffer, with blinking lights and happy faces and all that. So again, you want to make sure that when you look at these things, you understand the relationship of a buffer. So as we talked about, a buffer needs to either be a weak acid and its conjugate base, or the salt of its conjugate base, or it needs to be a weak base and the salt of its conjugate acid. Remember, a buffer itself cannot be a strong acid or strong base involved. So again, if you look at this guy, which is NH3, you hopefully should recognize that as a weak base. And again, it has like a Kb value of like 1.8 times 10 to the minus 5. And if you look at this, again, this is ammonium chloride. And that, again, is a salt that's really going to break apart into NH4 plus and Cl minus. So what we're talking about in terms of the buffer part of this really is the NH4 plus and the NH3. So this is really our two parts of our buffer that we got basically going on in this particular problem. So again, they may not always, kind of nicely tell you, hey, it's a buffer. So you do want to kind of think about these things when you see it given to you and see if there is a relationship between these two. The other way you could kind of look at it as well, since I decided to give you the Ka value for NH4 plus, that would obviously tell you that this is sort of a weak acid. And then in that case, this would be its conjugate base. So, it works out the same. But, those are two ways, again, you could sort of visualize or recognize that you're sort of dealing with a buffer. And as soon as you're able to recognize you're dealing with a buffer, which is really that common ion thing, again, the Henderson-Hasselbalch equation really should sort of come to your mind to use. And again, if you don't want to, you could always just go into that ice table like we've talked about before. Any questions up to there? All right. At this point, since we know it's a buffer, really, I think this is sort of the easiest approach. So we could go right into the Henderson-Hasselbalch equation, even made easier because I did give you the Ka value in this particular case. So we can go, the pKa is minus the log of the Ka value. And that would get us minus the log of 5.6 times 10 to the minus 10. And that gets you, I want to say, what do I want to say that is there? Minus the log of 5.6 to the minus 10. Looks like, not that, minus the log. Bad calculator, try that again. There you go. 9.25 looks like our pKa value. And that means we can go directly into the Henderson-Hasselbalch in this case, 9.25 plus the log. Again, we want to make sure we understand which one's our base. So the NH3 is our base. And again, based on what I gave you, which was that this is the Ka for this guy, that should tell you that that's the acid part here of the buffer. So again, you don't want to overlook those little kind of clues that you can find in the problems. We're going to take our base, which is NH3. So that looks like it's 0.3 divided by 0.36 in this particular case. And that looks like we end up with an opening pH for this buffer of, it's like 9.17, which is definitely a basic buffer here. And as you can see, even though it's a basic buffer, the Henderson-Hasselbalch equation worked just fine. We just want to make sure we were using the pKa value and we did the base over the acid. Any questions on that there? Now, again, this might be a situation where, you know, because NH3 is involved, maybe you're not given, you know, the Ka value, but maybe you're actually given the Kb value here, which could happen. So this might be a situation where somebody would use perhaps that other equation, that POH is equal to the pKb plus the log of the acid over the base. Here, the pKb would be minus the log of the Kb value, just to kind of show you, again, the other sort of approach, because it probably is maybe common to be given the Kb value in this particular case. If we do that, minus the log of 1.8 to the minus 5, 4.74 would be our pKb value, which means 4.74 plus, and remember that on this one, in addition to this being the pKb, it's actually the acid on top and the base on the bottom. This case, we would want to do the NH4 up on top, which would be 0.36, 0.3. And if we do that, 0.36 divided by 0.3, take a log action and add 4.74 to it. That's going to give us a POH of like 4.82. Remember, though, if you do use this equation, that's the POH, not the pH. So our pH would then be 14 minus 4.82. And we end up with, not that, 14 minus 4.82. We end up with 9.18. And you can see it's slightly different. And again, it's just a little bit difference on the rounding, the Kb value versus the Ka, but essentially the same number. So again, that's sort of an alternative approach that sometimes people will use. And again, you could use this, you know, if they happen to give you the Kb value. Your other option is if they happen to give you the Kb value here and you want to use the Henderson-Hasselbalch equation, you could use that other relationship that we saw as well, that the pKa plus the pKb is equal to 14. So you could find the pKa value by taking 14 minus the pKb, which would be 14 minus our pKb value of 4.74. And gets us 9.26. Again, just slightly different because of the Ka, Kb value, but that would get you here. And then you could go obviously into the Henderson-Hasselbalch as well. So, there's a few different sort of approaches. You could see that perhaps the easiest approach is really just going into the Henderson-Hasselbalch up front, because it usually is what you're asked for, which is the pH. Any questions on any of those sort of ways to solve the first part of the question? And again, if I was to do it, I probably would go this approach, obviously, the first way.
I have a question. So you're saying that first part of finding where we get the 9.17, that's what it's asking for the buffer solution, but then that second part is also a different way we can solve for it.
Exactly. So the second part's a different way, because sometimes what you'll see, especially in some books, and I don't know if your book does it or not like this a lot, but some textbooks do. What they would recognize on this buffer is as a basic buffer. So because it's basic, they would take more of the basic approach here, like the one I'm just circling there, with the POH first and then go to the pH. But you really do get the same answer anyways. So like I mentioned before, it's probably best just to go right into the Henderson-Hasselbalch, because it will work for acidic, basic, or any type of buffer really, and that's usually what you're asked for. There's nothing wrong with going on this sort of boxed approach I did there on the second way. It's just an alternative way that sometimes people will solve these problems because they're dealing more with a basic buffer rather than an acidic buffer. And you can see you pretty much get the same answer. The difference here is just really some rounding we did on the Ka and Kb values, but it's pretty much the same thing.
Okay, and so then if it's setting to calculate for a POH, would we then just do it that second way first?
Again, you could, but alternatively as well, you could still do it the first way and then subtract 14.
Oh, okay.
Yeah,
Gotcha.
so I personally think, like I said, in most cases when you're dealing with buffers or something like that, or even like we'll see this again, like when we deal with titrations and stuff. Most of the time we're not usually asked. You could be, but most of the time in practical application, you're usually asked about the pH. So that's usually the value most people are sort of interested in. So that's why I say you could go right into the Henderson-Hasselbalch equation. The only cautionary thing would be you could come across a problem like this one where I gave you the Ka value, but they may actually just give you the Kb value. So, that's why sometimes people will take this approach in textbooks, because they kind of give you that Kb value, and it's just a little bit easier to go sort of this way. But you could just as easily get the pKa value and stick it into the Henderson-Hasselbalch equation and get the answer, because again, you're usually looking for that pH value. But it's also a very common approach going the POH way because it's basic. I personally just don't see the value of it in probably 99% of the calculations you do, because probably in 99% of the calculations they're going to ask for the pH anyways. So you might as well just get right there to begin with. The only difference is you just want to make sure in that Henderson-Hasselbalch that if you were given the Kb value, that you do convert it to the pKa, so you have the right value, and that it's always, when you use Henderson-Hasselbalch, the base over the acid. So those are two important things to remember. And it was really sometimes only an issue when you're dealing with sort of basic buffers, because they sometimes will give you, like I said, the Kb value versus the Ka value, or you might only be able to maybe find the Kb value in the table or something like that. So that's where you could quickly use this to get you to the pKa value, and then you could go into the Henderson-Hasselbalch equation. Other questions on that?
Also one more question, sorry. But for the basic buffer, how did you know that it was a basic buffer? Was it because of the 9.17 on the pH scale?
Yeah, so when we look at these two things, really the NH3 is a weak base, so that's just something that you might know off the top of your head. And secondly, like I said, it is common that they might actually just give you this value and not give you the Ka value. So when you would see that, you'll know, oh, I'm dealing with a weak base. It's probably going to be more of a basic pH than an acidic pH, rather than if you looked at, say, the previous example or a couple of the previous ones we did, where we dealt with like formic acid, it was more of an acidic pH. We dealt with acetic acid, was kind of the guy that had the K value. It was more of a acidic sort of pH and stuff like that. So just being able to recognize that NH3 is evolved, which is definitely a weak base, is probably why you might realize that this might be more of a basic buffer. Other questions? And like you said as well, when you calculate the pKa value, you kind of see that 9.25, or not, whatever it is, 9.25. And definitely when you calculate the pH, it's 9.17, which definitely is a basic buffer. Other questions on that? Okay, so that's the first part of the calculation, obviously. Now, the second part of the calculation is, now that we have sort of this buffer made, we have made basically 80 milliliters of it. So in part B here, we have basically now 80 milliliters of this buffer, which does contain really those two things, NH3 floating around and NH4 plus floating around as our buffer. And again, we can kind of think of it the same way. This is the base part of the buffer. This is the acid part of the buffer. And now to this, what we're going to do is take 20 milliliters of sodium hydroxide. We're basically going to add it in. So as was sort of an earlier question, because we are adding sodium hydroxide here, it is a base, we should expect the pH to go up, right? So that's a good way to kind of maybe check your calculation when you're all said and done. The second thing that's also important is we are now adding volume, right? So we're taking 20 milliliters of the sodium hydroxide and we're adding it to 80 milliliters of the buffer. So this also should signal to you that you need to do an ice table. And the purpose really of the ice table is to figure out what's going to happen really to our buffer. You know, how is it going to be affected by adding the sodium hydroxide to it? The other important thing is that since we're adding volume, we definitely want to do this table in moles. Again, because whenever we're adding volume, that molarity is going to change. So you want to do that initial ice table in moles. And the third important thing to recognize is what is going to happen when we add that to the solution. So first thing hopefully you can recognize at this point is sodium hydroxide is definitely a base. So when it is added to the buffer, it is going to seek out and react with the acid part. So those are your two guys that are essentially going to react with one another here. And that's going to really be the basis of your ice table. Any questions on that? So we do need moles for this ice table. So that might be a good place to kind of start with here to figure out the moles of everybody. And in this case, the volume is not being held constant. So to figure out the moles of our sodium hydroxide we are adding, we would take the volume of it, convert it to liters. So that's 0.02 liters times the molarity of the sodium hydroxide, which is 0.05 moles per liter. Those are going to cancel. And that gives us, in terms of sodium hydroxide, we're basically going to be adding 0.05, which is our 0.041 moles here. We also want to do that for everybody else that's there. We want to figure out the moles of our buffer. So for our NH3, we have 80 milliliters of the buffer. So that's going to be 0.08 liters times the molarity of our NH3, which is 0.3. So 0.3 moles per liter. And that will get us 0.08 times 0.3 gives us 0.024 moles of our, well, this top guy is sodium hydroxide. This guy is our NH3. And also something that sometimes messes people up is the volume of the other part of the buffer would also be 80 milliliters. So remember, we have 80 milliliters total here of our buffer we're starting with. And that's basically the volume for both parts of it. So the moles of the NH4 plus would be 0.08 liters times the molarity of the NH4 plus, which is 0.36. So that's going to be 0.08 times 0.36 on that. And we'll go with what we got there. 0.08, there we go, times 0.36. Go with 0.0288 moles of NH4 plus there. Any questions on that? I guess I could round that to 0.029. Any questions on how to get the moles? Okay, so now we could do really part B, which again is our ice table here with the reaction. So we've already just established that is going to be the NH4 plus that's going to react with the sodium hydroxide. So that will be the basis of our reaction, NH4 plus. And again, if you want, you can leave, and I'll leave it in there. That way we can see where everything is. It's actually NH4Cl. Again, the Cl really a spectator ion, but we'll leave it in. Plus our sodium hydroxide we're adding. We're going to get some water there, and we're going to get some sodium chloride, and we're going to get a couple other things. So we have water, sodium chloride, and some NH3 happening there. That's a lot of stuff. So again, positive, negative, and really this guy is going to donate the H plus over here. That's where the water comes from. That's going to leave this guy as NH3, and then our sodium and our chloride will come together, in case you're curious where everything came from. All right, so we're going to do this guy in moles, as we talked about. Kind of clear it out there. So initially, I probably should have paid attention there. An NH4 plus, I think I'll round it at this point. I believe it was 0.029 moles. Our NaOH was 0.001 moles. Again, water, not important, not going to be involved. Again, our sodium chloride, really not important because it's not going to be involved. It's a neutral salt. It is the NH3 that's important, and that was, I believe, 0.024 moles. Any questions on that? Just like before, because this is a buffer, we would expect all of the sodium hydroxide to be used up. So we actually do know the change. It's going to be minus 0.001, minus 0.001, and plus 0.001. By the way, when we look at this number versus this number, this is what we added, and it's basically less, which means it's kind of like a limiting reagent, the sodium hydroxide. So that's how we know it gets all used up. It's got to be the smaller number, right? Otherwise, you get a negative number, which would not be good. We will then get at equilibrium 0.029 minus 0.001, going to get us 0.028. And remember, these are moles. That's going to get all used up. Again, here, because water is not really involved, I'm not going to write any numbers here or anything like that. Same thing with the sodium chloride. So I don't try to use it in the wrong spot. That's going to give me 0.025 moles of this guy. First off, any questions on the ice table here? All right, so super important really at this point and very, very good practice, although in reality, it actually doesn't make too much of an issue if you use the Henderson-Hasselbalch equation, but good idea to convert these guys back into molarity at this point. Again, remember that in this case, the volume was not held constant. So our total volume at this point, we started with 80 milliliters of the buffer. We added 20 milliliters of the sodium hydroxide. That gives us a grand total of 100 milliliters. So we're going to take each of these and divide it by 0.1 liters to convert it back into molarity at this point. And that gets us 0.028 divided by 0.1. 0.28 molar and 0.25 molar at this point. Any questions up to here? All right. So you may get to this part of the ice table, hopefully. And at this point, you may be wondering, I'm not really sure what to do next. So we are looking for obviously the pH in this case. So the ice table can be very helpful to you. If you look at the ice table and see what we got left at this point, we have some ammonium chloride and we have some NH3. And that again is a weak acid conjugate base or weak base conjugate acid, however you want to look at it. So this is still a buffer at this point, right? These two guys, let's draw the arrow this way. These two guys here are a buffer. And that means to calculate the pH, because it's a buffer, we could go back into our Henderson-Hasselbalch equation. Or again, you could use an ice table if you wanted to. The pKa value is going to be the same as the first one, so still 9.25 plus the log again of our base. So again, being able to recognize which one is which is really important. So this again is our base here. This again is NH4 plus, which is our acid. And again, in this particular problem, because of the way it was given to you, you would know it's an acid because of the Ka value that was given. And that means that we are going to take the 0.28 divided by, no, you're not. I did that backwards. You can take the base. Try again. We're going to take the 0.25, which is the base, 0.25 divided by our acid, which is 0.28. And in this particular case, that will then get you 9.20 as our pH after we added the sodium hydroxide to it. And we can make sure it does make sense because before we added it, we were at a pH of 9.17. We added base, the pH went up. So that does sort of make sense in this particular case. Again, you could do an ice table if you wanted to and solve it using the Ka value. Could even do a KB table if you wanted to and do it that way. But, you know, this again is probably the easiest approach. Question on that one there.
Professor?
Yeah.
What would you do in terms of solving the pH if we run out of the buffer, but we still have the base left?
Yes. So it's a good question, and it's actually something I was just going to talk about in 1 second. So hang on to that question. I think I'll answer it. I was going to kind of use an example that we did previously as to what will happen. And it's basically about sort of that buffer capacity we were talking about. So give me 1 second. We'll talk about that. Other questions though on this one? Okay. Questions on how to solve buffer problems. Again, as well, you could have, again, I don't want to give you a bunch of different ways to do this, but there are different ways. But, you know, if you want to use that pOH equation, you could also use an ice table to get to the pH at this point. So, you know, there's a variety of ways to get there. Probably the most straightforward, maybe the least room for error would be to try to use the Henderson-Hasselbalch equation here. And again, we could do that because we are dealing with buffers. As I mentioned before, it is really good practice to convert these guys back into molarity after the first ice table. To be truthfully honest with you, it doesn't make a difference if you do use the Henderson-Hasselbalch equation because the difference in volumes will cancel out here. So you actually could go moles and moles here if you wanted to. You could have done the 0.025 moles divided by 0.028, and it actually would work out okay because you're using this Henderson-Hasselbalch equation. But you know, you should convert it back to molarity because there will definitely be situations coming up where you do need the molarity. And if you don't convert it back to molarity, you'll get the wrong answer. So just really good practice just after the first ice table where you do everybody in moles to convert it back into molarity at that point. And, you know, it just makes it a lot easier to figure it out. All right. Other questions? Okay, our buffers in general. So obviously you need to be able to figure out what a buffer is, how it works. You need to be able to figure out the pH of a buffer after you make it. You also need to be able to figure out, the pH of a buffer after you add either acid or base to it. Any questions? Okay, so let me do this, and I think it will answer your question. Why don't we just go back and use the, let's take a look at the example we did previous to this one, just because that had a little bit easier, straightforward numbers. So let's go back to that one where we had the acetic acid, for example, and sodium acetate buffer. And I think it was the one we just did. So I think it was like maybe it was 1 molar in each of those, I think. Yeah. So we'll assume that it's again 1 molar of this guy and 1 molar of this guy, and we added some HCl to it, right? And in the case of the problem, I think we added 0.1 HCl or something, I think. So 0.1 molar HCl. So we'll do the same thing. We'll just assume in this case, just like in that first problem, that all the volume stays at 1 liter, just to keep the numbers sort of easier to see. So let's say we did it when we added the 0.1 molar HCl to it, and we saw that obviously the pH went down in that particular case to 4.6 something. But what happens though if you, in terms of say buffer capacity, you weren't really following the instructions and you decided, hey, I grabbed the 18 molar HCl and added it to this buffer, right? So let's just kind of go through the ice table and see really what will happen, in terms of the pH in this particular case. Will it be able to maintain, the pH it started with? And a reminder, that example we did, which was the previous one, our pH of our buffer to start with was like 4.74, right? All right, so you decide I'm going to grab that 18 molar and I'm going to add a liter to it, which is a lot. So just like before, the HCl would react with the sodium acetate. And just like before, we would produce, right, some acetic acid. And we would produce, obviously, some sodium chloride. Now, just like we just did in this problem, just like we talked about in the previous problem, we do want to do our initial table here, obviously in moles. So again, just to kind of keep the numbers pretty simple, we're going to assume 1 liter. So to figure out the moles of our HCl, we would times that by 1 liter, would give us 18 moles of HCl we added to this buffer. Our sodium acetate, we added 1 liter. So obviously in this case, we would have 1 mole of our sodium acetate. And obviously our acetic acid, we added 1 liter. So we would also have 1 mole of this guy as well, and 0. So this would be the setup that would happen, if you grab perhaps the wrong bottle and you weren't really following directions and you made a buffer like this that wouldn't work. What would happen when we get to our change part of the ice table is the change would actually be the sodium acetate in this case. Because what happened is we added way too much of our HCl in this case. This now becomes like our excess reagent. And what it ends up doing is turning this part of our buffer into the limiting reagent, right? So the change part actually would be -1 here, -1, right? Because you couldn't do -18. Otherwise, you would end up with a negative concentration or moles. You can't have that. And you would actually end up with +1 on this side, which means what would essentially happen at this point is we would end up with 17 moles of our HCl, none of this guy. We would end up with 2 moles of this guy, right? We then can convert this back into molarity, assuming 1 liter in this case. We'd have 17 molar of this guy. We would have 2 molar of this guy. So a couple of things basically would just happen, which I think was the question that was just sort of asked. Now, what we are left with at this point in this process is we're left with acetic acid and we're left with HCl. These two things are not a buffer, right? Those two things are not related to each other. These two guys are definitely not a buffer. So what do we really have happening in this solution, right? Because we blew away pretty much all the sodium acetate. So when we started, before we added the HCl, we had acetic acid floating around. We had a little bit of H plus from the acetic acid. We also had some sodium acetate blowing around. When we put in our HCl, what it essentially just did was take out all of that, right? It's all gone now. And we've now added more H plus from the HCl. We also have more Cl minus, but more importantly, we added a bunch of H plus. Right? So what we actually have in this solution at this point is actually two acids, right? They both are going to be contributing to the total H plus concentration, right? Out of the two, probably the HCl that you added is going to be the major contributor, right? Because it just needs to go for a swim to produce that H plus. But the acetic acid will still, do its little reversible reaction and produce some H plus and see it and acetate a little bit. But by having all that H plus, it's also going to force the equilibrium back the other way, right? And kind of keep it together. So the HCl in that price is probably going to be the major contributor. If you really want to get technical, you could try to figure out as well how much H plus is coming from the acetic acid that's still there. You would have to do an ice table where you would have this guy from here and this guy as well. And you could add up all the H plus together and get the pH of that solution by adding up pretty much all the H plus that's being contributed by the acid and all the H plus that would be contributed by the weak acid. Again, it's going to be a little bit less for the weak acid because of the presence of all that free H plus really going to shift the equilibrium back this way and keep this mainly together. And that's why I said probably your major contributor at that point would be your HCl. The acetic acid would be contributing a little bit, but maybe not all that much because of that. So this is why if you don't make your buffer correctly, or you add something that is way too strong for your buffer, you basically could blow right through the buffer's ability to maintain the pH. What would we see in this case? Well, we would definitely see our pH go from 4.74 super down near zero probably, or even past zero, because we basically blew through the buffer. It's not able to handle that much HCl in this particular case, and we would see a tremendous jump in the pH in this case. And the ultimate sort of understanding of what we're talking about is when you make a buffer, and you can kind of see it in the ice table, really your buffer only has a certain amount of moles that are available to react with any more acid or base that you put in there. So if you make a buffer where, it's not able to handle the amount of H plus coming in from a strong acid or OH minus coming in from a strong base, you're going to run into troubles, and it really will not function as an effective buffer, because as this sort of table demonstrates, you'll basically blow right through your buffer and you'll see a pretty big pH. It'll be able to hang in there for a little bit, but at some point, if you just go back to that kind of picture I drew in lecture, if this is the acid part and this is the base part of the buffer, at some point, you're just going to eat up all that base part, and there's not going to be no base part really left in a significant amount of quantity to basically prevent that pH from moving, because you're just going to add a lot more H plus. And to maybe answer your question specifically, the same thing would happen, if you did the same thing and you added like too much sodium hydroxide, right? If you added too much sodium hydroxide, again, it would react with the acetic acid and make your sodium acetate plus whatever we got there, water. So same idea, say we had the 1 mole of this guy to begin with, the 1 mole of this guy. Heck, say even added, say 4 moles of this guy. Same idea when we do the change part, This guy now would become the excess reagent. This guy would become the limiting, and the change would always be the smaller number. And what we see is we will end up using up all of our acid in our buffer and be left really with two bases at this point, right? We have sodium hydroxide that's left over, which is a strong base and going to contribute a ton of free OH minus and probably be the major contributor. While we have acetate, which is a salt that will go through hydrolysis, right? And going to accept the H plus and make some acetic acid and OH minus. So again, remember that out of the two here, probably the major contributor at this point would be the sodium hydroxide. And again, in this case, we would see the pH go up by a lot because we basically blew through all of the acidic part of the buffer, and there's really nothing left other than you're just now dropping OH minus in there, and it's going to cause the pH really to go up a lot. Question on that? Other questions on buffers? I hope that answers your question. I think that's what you were kind of asking, I hope.
Yeah, it did. Thank you.
Any other questions on buffers, how to do calculations, how they work? Okay.